الفريق العراقي. فاستمر التدريب لمدة أسبوعين، وتدربنا أيضا في 2008 و2009. بعدين حصلنا على منحة من وزارة الدفاع الأمريكية، وعملنا كثير من ورشات العمل في أربيل، وأكثر الأخوة العراقيين اللي موجودين حاليا في الوزارة شاركوا بها. بعدين صار المشروع مالت الأشري، واللي هو اشتغلنا مع مديرية المياه الجوفية بشكل أصلي، وكان دكتور صادق ممثل عن العراق ودكتور ظافر، وسوينا مابينج للعراق كله، وكان الفند جاي عن طريق اليوروبيان يونيون اللي اعطوه لليونسكو. فتاريخ جدا قديم وتاريخ جدا حافل. وأنا أشكر معالي الوزير للدعوة اللي وجهها لنا بالمشاركة في هذا المؤتمر المهم والذي لم يسبق له مثيل، وأنا شخصيا أتشرف بالمشاركة مالتي وإعطائي الفرصة بالتحدث. ويا هذا بسبب الوقت أقدر أحكي لمدة أيام. أقدم المهندسة الأقدم حمدية أن تتكلم عن المشاريع اللي سويناها بال2019. اجونا مجموعة من الأخوة العراقيين إلى أمريكا، وكانت المنحة أيضا من وزارة الخارجية الأمريكية. مشكورين على هذه المنحة، أنه لتدريب الكادر العراقي. بال2008 وال2009 دربناهم أنه كيف يستخدمون البيانات، فكنا إحنا نحلل البيانات الناتجة عن الريموت سنسينج ونخليها على الويب سايت مالتنا، وأيضا تدربوا على كيفية كتابة التقارير الهيدرولوجية اليومية.
دكتور اعطينا مجال.
سوري. بال2019 اجانا فريق، اكثر من فريق عراقي، تدربوا على منتجات الثلوج، وتدربوا على كيفيه حساب النتح والتبخر الET، وايضا اجوا جماعه للتدريب على الايكونوميك اسسمنت مع نيو مكسيكو ستيت يونيفرسيتي، وكان دكتور وورد ودكتوره دينا سلمان موجودين هناك دربوا اخواننا العراقيين.
دكتور انطينا عطوه، نريد نسلم عليك.
العفو، عفو سيادة الوزير، تفضل.
أنا أشكرك حقيقة دكتور على كل ما قدمته سابقا وتقدمه حاليا وما ستقدمه مستقبلا خدمة لبلدنا، ودعمك هذا حقيقة احنا ممنونين منه، ونشكرك على كل الجهود وكل المعلومات وكل الورش العمل التي حقيقة خدمتنا. وأنا أتشرف أنني كنت أحد المتدربين في هذه.
لو قطع الصوت. الو. 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 الو.
Saud, we can hear you.
Okay, well, I don't hear anyone. Is there someone talking?
Mr. Bell, I hear you. You can go ahead.
Okay. ما أعرف، كان معالي الوزير يتكلم، فما أعرف إذا خلص.
نعم، هاي ويقصد.
ألو.
ليه يسمعك؟
دكتور أنا أشكرك وعاجز عن شكرك على كل ما قدمته وستقدمه وما زلت تقدمه لتنمية قابليات كوادر وزارة الموارد المائية من معلومات مهمة حقيقة أحدثت طفرة في إدارة الموارد المائية من ناحية التوقعات الأمطار. هذه التطبيقات التي حقيقة تدرب عليها الكادر. احنا ممنونين من حضرتك ومن كل ما قدمته دائرة المسح الجيولوجي اعتبارا من مديرها التنفيذي إلى بقية الأخوة الخبراء. شكرا جزيلا دكتور.
شكرا جزيلا معالي الوزير، وإن شاء الله نبقى بالخدمة وهذا بلدنا. وأنا جدا ممنون وحصل لي الشرف بالحقيقة أن أتعرف عليك والأخوة والأخوات الباقين العراقيين، وأعتقد التدريب مالنا نتج عن نتائج جدا جيدة بسبب تفهم الكادر العراقي. وهسه أحب أن أقدم المهندسة الأقدم حمدية أن تحكي عن التدريب اللي صار بال 2019 وكيف أنه إحنا انطينا التقنية للفريق العراقي بدل ما إحنا كنا نسويها التحاليل ونقدمها لكم عن طريق الويب سايت. هسه الفريق العراقي نفسه هو يقوم بإنتاج هاي المنتجات كلها ويكتب التقارير الخاصة بها. مهندسة حمدية الفلور إليك.
السلام عليكم سيادة الوزير، السلام عليكم الحضور جميعا. شموتي
قاعد نشوف هالبرزنتيشن ست حمدية.
انت مشكلة سوي انت هنا. لا مطار.
يلا اوكي بس قولي نيكست.
اوكي نيكست سوي الورا. طبعا استاذ سعود حكى على البدايات اللي كان بيها التدريب اللي هو من المنحه الامريكيه بسنه 2008 و2009 و2010 واللي كان بها هو رئيس الفريق استاذ مهدي. وبالبدايه كانت هاي عباره عن الاطلاع والتدريب على برامجيات ثلاثه اللي هي التوقعات الجويه بالامطار المستقبليه والثلوج والماء المكافئ للثلوج، وايضا حساب النتح تبخر والموديلات الخاصه بكيف نراقب مناسيب وخزن السدود اللي داخل الحوضين نهري دجله والفرات. بعدين اكملت من خلال موجب منحه من السفاره الامريكيه بال 2019 ايضا اكملنا التدريب، لكن هالمره كان شويه موسع، يعني التدريب على الموديلات كيف انه وبلشنا باربع موديلات اللي هي التوقعات الجويه ومعادله موديل التبخر نتح وموديل المياه او تحديث دراسه خاصه بالمياه الجوفيه ودمجها باشري، وايضا الايكونوميك اوبتمايزيشن. واكو بعد عندنا الدامز مونيتورنج وانشاء موقع الكتروني مثل الموقع اللي دا نسحب منه كنا من يعني نسحب منه المنتجات الخاصه بالتوقعات الجويه اللي كان هو تابع لليو اس جي اس. طبعا هاي المنتجات هي من احنا اطلعنا عليها، كان هذا طبعا جديد، هذا ما كان متبع بالعراق. فمن شفنا انه يعني يعتبر هذا من المنتجات المهمه والضروريه، لان من خلالها نعرف كيف طبيعه السنه المائيه، وايضا من خلالها راح يعني نتوقع ايش قد راح تجينا ايرادات، او هاي السنه هي دراوت او ويت يعني، ونضع على اساسها الخطط التشغيليه اللازمه. نيكست بليز. من خلال تمرينها صراحه انا راح اتناول بس التوقعات الجويه، هذا احدى التدريبات. تم هذا التدريب لازم يسوون لنا سكريبت، هذا السكريبت هو بلغه البايثون اللي هي على اساسها هي راح يتعامل ويا الاقمار الصناعيه والموديلات الاخرى اللي تشغل جميع الموديلات. فسووا لنا سكريبت خاص بالعراق، يعني هو هذا السكريبت هو جزء يرتبط بالماستر كونفيجريشن اللي هو خاص باليو اس جي اس. هذا طبعا خلينا كل الاشياء اللي تخص العراق، ونربط هذا السكريبت بالقمر اللي ينزل المنتجات من الاقمار الموديس واللانسات. نيكست. هذا هو نموذج يعني قسم من السكريبت اللي خاص بالعراق اللي يرتبط بالماستر الرئيسي اللي هو تابع لليو اس جي اس. من المنتجات اللي احنا تعلمنا عليها واللي هي مو مثل قبل نستلمها، لا هسه احنا بموجب كوماند برومبت احنا راح ننزلها بايدينا يوميا الساعه مثلا ب8 او ب9 عن طريق انترنت جيد، راح اقدر انزل عن طريق اعطيه كومنت، هو راح ينزل لي جميع المنتجات وبمختلف يعني الاوبشنات، او صوره او جيوبل او تاك او يعني هذه. فمن ضمنها هذه الصوره، هاي مثلا مال اليوم، وهاي الايام البقيه هي الايام القادمه. يعني من خلال هاي نشوف الامطار، طبعا كل مطار هي كل لها ليجند معين، لها اللون، الى كميه الامطار الساقطه. طبعا احنا نراقب هاي الامطار يوم ورا يوم الى ان تصل مثلا قبل 3 ايام نتاكد انه هاي المطره جايه، راح على اساسها احنا ناخذ اجراءاتنا، اما تقليل مثلا الاطلاقات من السدود، هذا لان اكيد له تاثير في خزن مياه، وايضا في يعني المحافظه على مستوى المياه في الانهار. ايضا من المنتجات اللي احنا ننزلها بايدينا هي منتجات مساحه خارطتين مساحه انتشار الثلوج للحوضين، حوضي دجله والفرات، وايضا كل واحد هذا يقارنها مثلا ويا العام الماضي، ويقارنها ويا مثلا هذه يقارنها ويا مش زين يقارنها مثلا ويا العام الماضي، او يقارنها ويا المعدل. ومن خلال هاي احنا ببرنامج جي اي اس نروح نرسم هذاك الكيرفات اللي تعطينا النسبه المئويه لانتشار الثلوج، انتشار يعني مساحات فقط هذه. يعني هذه وهذا طبعا لكل 17 حوض، ليس حوض واحد، هذا واحد منهم. الحوض هو الجريتر زاب، اكو سيلوبي، اكو سعرت، يعني اللي داخل مثلا داخل تركيا وبداخل العراق واللي بايران. ايضا منتج ثالث هو يعطيني السنو ديبث، اعماق الثلوج، وايضا ليجند لكل واحد عمق. هذه ايضا بعدين من خلال هاي راح نيكست وراها، هذه بعدين هي 17 حوض، هذا نموذج من الحواض اللي هي بتركيا والعراق وسوريا، تركيا والعراق وايران الاحواض اللي تكون، فنطلع منها كيرفات ايضا عن طريق الجي اي اس. طبعا هذا ما كمل التدريب لان الوقت صار كلش ضيق، فتعلمونا على موقع الروح نطلع منه هذه 17 حوض، كل واحد يطلع لي مثلا انا ايش اريد يا سنه، مثل هالسنه ويا المعدل العام ويا اعلى شيء وعلى، ومن خلال هذا احنا نسوي جدول. بليز فرا نسوي جدول مثلا سنه 2020 ويا السنه اللي قبلها ويا الافرج، وعلى هالاساس ايضا نشوف احنا ايش قد راح تجينا سنو ووتر اكويفالنت، الماء المكافئ للثلوج. نعم
حمدية، اكو مترجم لازم تنتبهين له، انت تتكلمين
كله عربي،
اكو مترجم لازم تنطين مجال للترجمه.
سوري، مو هو اللي انا محددني ب5 دقائق دكتور سعود. بنسوي هذا الجدول ل 17 حوض، الاحواض اللي تجي السميشن مالتها مال الماء السنو ووتر اكويفالنت يعني يجي للدجله، والاحواض اللي تجي للفرات، والاحواض الجوه اللي هي داخل ايران اللي تجيب للكارون. فعلى اساس هذا هم احنا نشوف طبيعه السنه المائيه تفيدنا طبعا، لان حتى انه ايش قد راح تجينا في ايام الثالث والرابع او الخامس، ايش قد راح يجينا مي، يعني وعلى اساس هذا تباعا هو ايش راح يفيدنا بوضع الخطط المستقبليه لاداره وتشغيل السدود والسدات. شكرا جزيلا.
شكرا ست حمدية على هذا المحاضرة اللي بينت بشكل ما أعرف شلون قدرتي تسويها بشكل هيك مختصر بدقائق أنه توضحين التقنية اللي تعلمتوها. وأني بصراحة جدا فخور بالكادر العراقي اللي إجا والتقنية اللي موجودة عندهم، وإن شاء الله التدريب مالنا مع وزارة الخارجية الأمريكية لحد الآن ما انتهى. بالحقيقة كان مجموعة يجونا في آذار الماضي وكانت بطاقة السفر محجوزة لهم والفنادق، بس للأسف اجى البانديميك وكنسلنا كل شيء. بس الحمد لله أنه إن شاء الله عن قريب ينفتح السفر ونلتقي بالكادر العراقي الباقي لتدريبهم على باقي التقنيات. Mr. Chairman, now I think I should start my presentation.
Very good. Sodoma will now present on monitoring and forecasting dust storms in Iraq.
Thank you. Let me share my screen. It won't let me stop the picture, just Do you see the presentation?
We do. We see the presentation. It is not in presentation mode, but we do see the slide. Yes.
Okay, do you want me to put it in presentation mode?
If you are able, there you go.
Okay. Okay, أعتقد أكمل بالعربي إلى to the extent possible. البرزنتيشن مالتي أنه راح أحكي عن العواصف الرملية والترابية بالعراق. البرزنتيشن هاي حضرت من قبل زميلي بروفيسور بات شافز واني، البروفيسور في جامعة نورثرن أريزونا يونيفرسيتي في ولاية أريزونا. مثل ما نعرف العواصف الرملية والترابية بالعراق ازدادت حدتها وتكرارها. يعني أتذكر بالستينات والسبعينات كانت عاصفة ترابية واحدة بالسنة جائز توصل لبغداد جائز ما توصل. هسه وصلت إلى 10 إلى 15 عاصفة ترابية بالسنة. وحتى قسم من العواصف أنا كنت موجود بها في بغداد بال2008 و2009. فهذه صور من المودس اللي هو واحد من الأقمار الصناعية الأمريكية. بال2009 حتى في نهاية شهر حزيران ضربت العراق عواصف ترابية ورملية استمرت لمدة أكثر من أسبوع. وهاي الصور اللي دا تشوفوها من 3 آب و4 و5 العفو تموز 3 تموز و4 و5 عواصف ترابية كلش كثيفة. حتى في وقتها كانت زيارة مخصصة إلى الوكيل في حينه وكيل الرئيس الأمريكي مستر جو بايدن، واللي هو الآن رئيس الولايات المتحدة الأمريكية، وانجبر أنه يكنسل الرحلة مالته بسبب العواصف الرملية. وإن شاء الله أنه يزور العراق والأجواء تكون صافية. بالنسبة للعواصف الرملية والترابية مو فد شيء جديد، وبدأ يتزايد مو بس بالعراق بس في مناطق أخرى كثيرة بسبب التصحر، واللي هي أسبابها كثيرة. التغير المناخي، قلة المياه، قلة الأمطار، قلة المياه السطحية. فهواي أسباب إلها، لكن المسألة أنه إلها حل جذري. فبالنسبة لنا الوضع اللي طبعا العواصف الترابية والرملية درست بشكل كثير، وهسه أشوفكم قسم من الأمثلة. بالنسبة لنا نعتقد أنه الغطاء النباتي هو أكثر عامل محدد لمراقبة وتنبؤ العواصف الترابية. صحيح بيانات الإرصاد الجوية هي مهمة جدا، لكن الغطاء النباتي هو أهم. فإذا استخدمنا الغطاء النباتي ودمجه مع بيانات الساتلايت وبيانات الإرصاد الجوية يكون أكثر دقة. فهذا الطريقة اللي احنا انه اذا توفرت لنا ان شاء الله مصادر كافية، انه العمل ايضا مثل ما صار العمل مع الفريق العراقي. ما اعرف الكلام مالتي يعني بطيء اناف انه للمترجمين. اوكي. فبالنسبة للفكرة مالتنا أنه أيضا نجيب فريق عراقي إلى أمريكا وندرب التقنية، نعطيه الموديلات والتول اللي يأهلهم، مثل ما شرحت المهندسة حمدية شلون اجوا لهنا وتعلموا الموديلات والتقنية، وهسه هم يقومون بإنتاج المنتجات مالتهم هناك. فعلى أساس نفس الشيء إذا توفرت لنا المصادر الكافية أنه نشتغل مع فريق عراقي ونجيبه إلى هنا ونعلمه الموديلات والتولز اللي راح نجي بيها. أجين العواصف الترابية درست بشكل جدا كثيف من قبل كثير من الباحثين. هاي الصورة اللي إذا تشوفوها السيركلز، هاي الدوائر الحمر، هي تقريبا مصادر، جزء منها مو كلها. وايا اكو مصادر للعواصف الترابية والرملية بالعراق، فهاي جزء من عندها تقريبا، هاي مكاناتها انه وين المصادر. فاذا اكو عندنا نبذة مختصرة عن ما موجود، يعني ما راح نبدي من الصفر، بل بالعكس راح نبني على الدراسات اللي موجودة والدراسات اللي صارت. فالخطة مالتنا أنه نبدي بساتلايت داتا اللي هي أكثر دقة من اللي استخدمت. مثلا الصور السابقة اللي شوفتكم إياها هي ماخوذة من، هاي الصور ماخوذة من مودس، واللي هو مو دقيق بالنسبة للسبيشال ريزولوشن. الدقة مالته 250 متر، هي هاي أكثر دقة، وتروح إلى 500 متر وإلى 1 كيلو. هاي نعتقد أنه مو دقيقة كافية لاستخدامها لمراقبة العواصف الترابية. فكثير من الباحثين العراقيين اشتغلوا على العواصف الترابية والرملية. هاي بس كم اكزامبل. ومثلا عندنا استاذ موزان والطائي اشتغلوا على بيانات من الارصاد الجوية من 1988 الى 2017، وشافوا انه 2008 كانت اكثر سنة بالنسبة للعواصف الترابية والرملية. أيضا دراسة قدمت من قبل أخوة عراقيين، مستر هاشم وعبد الجبار، استخدموا الميتيوسات، واللي هي الساتلايت الأوروبية اللي تعني بالإرصاد الجوي، وشافوا أنه بال 2011 18 عاصفة ترابية ضربت العراق، 18. فمن عاصفة ترابية واحدة إلى 18 عاصفة ترابية بسنة واحدة. فهذا طبعا أضراره جدا واسعة بالنسبة للقضايا الصحية، بالنسبة للقضايا المالية، وأيضا الحوادث المميتة اللي تصير على الطرق بسبب عدم الرؤية. الكادر العراقي أيضا اشترك ببحوث عن العواصف الترابية والرملية مع باحثين من المنطقة. هاي دراسة صارت بين الكادر العراقي والكادر الكويتي، أيضا استخدموا المودس ودرسوا من 2007 إلى 2018، وحددوا أنه أكو مناطق يسموها هات سبات اللي هي تنبعث منها العواصف الترابية والرملية. حاليا موجود أكو سنتر في برشلونة في اسبان أيضا يدرس بشكل مستمر، لأنه يأخذون الصور الجوية كل نص ساعة وكل 15 دقيقة ويقدرون يشوفون بها العواصف الترابية. فإحنا ما راح نبدي من الصفر، بل بالعكس نشوف اللي اندرس واللي قاعد يندرس هسه ونبني عليه. وأيضا زميلي بات شافز اللي هو في جامعة نورثرن أريزونا يونيفرسيتي اشتغل كثير سابقا في الجزء الساوث وسترن اللي هو الجنوب الغربي من الولايات المتحدة الأمريكية، واللي يعتبر أيضا مناطق قاحلة إلى شبه قاحلة. بالحقيقة أريزونا والعراق على نفس خط العرض، فتقريبا نفس الجو، نفس الكلايمت، أرد سماي أرد. فكانت بوقتها يعني العواصف الرملية والترابية شديدة جدا في ذاك المكان، بس راحوا للجذور مالتها وحلوا المسألة. هسه العواصف الترابية والرملية موجودة بس بشكل جدا جدا قليل، ما زادت مثل ما بالعراق. فالمهم أنه هنا نعالج الجذر، نعالج السبب اللي يسبب هاي العواصف الرملية والترابية. فالابروتش مالتنا انه نستخدم ساتلايت داتا اللي هي اكثر دقه، مثلا اللاندسات اللي هي 30 متر مكان ما 250 متر، السنتينل 10 متر. فهاي الساتلايت تعطينا اكثر دقه عن الغطاء النباتي، لانه كل ما كان غطاء نباتي كثير كل ما التربه تكون محميه، لما تيجي الرياح ما راح تصير عواصف ترابيه. فهذا الفرق بين اللي موجود وبين اللي احنا نفكر به نشتغل به مع الفريق العراقي ان شاء الله اذا توفرت المصادر، انه نستخدم اللاندسات، نستخدم السنتينل اكثر دقه بالنسبه للسبيشال ريزولوشن، وبوقتها نراقب الغطاء النباتي. اكثر الدراسات اللي صارت هي صحيح يستخدمون الساتلايت مثل ما قلت سابقا، بس ايضا يستخدمون بيانات الارصاد الجوي كشيء مهم اكثر من الغطاء النباتي. وراح اشوفكم بالسلايد الاخير. I kept the best to the last. ليش؟ انه بس البيانات الارصاد الجوي لوحدها ما راح تعطينا فكره جيده وصحيحه عن العواصف الترابيه والرمليه. How am I doing with the time, Bill?
You have 3 minutes.
Wow. All right. 180 seconds. That's good. فإذا بالنسبة إن الطريقة مالتنا إنه إحنا نركز على الغطاء النباتي، لأن كل ما كان الغطاء النباتي أكثر كل ما كانت العواصف أقل. هاي صورتين الفوق والجو ماخوذة في نفس المكان في ولاية أريزونا، واللي هي الجنوب الغربي من الولايات المتحدة الأمريكية، واللي بها العواصف الرملية. حتى على هذا الهاي واي اللي إذا تشوفونه هنا بالصورة اكو لوحات الكترونيه يحذرون العالم. كانت حوادث كثيره تصير، وحوادث يعني قاتلة بسبب عدم الرؤية تماما. بس هسه المنطقة راحوا للجذور مالت المشكلة وحلوها، وهسه تشوف العواصف الرملية قليلة جدا، وإذا صارت فتكون مو كثيفة. فهاي الصورة هنا اللي تشوف كل المكانات الحمر هي حقول. فالنباتات الغطاء النباتي بهاي الصور مالت الساتلايت يبين أحمر. فأكو فرق بين الصورة الفوق والصورة الجوة. فكل ما كانت حقول مهجورة وحقول غير مزروعة راح تكون عواصف ترابية. هنا هاي أيضا ساتلايت من اللاندسات 5. بالصورتين الفوق نشوف كل النقاط الحمر هو غطاء نباتي. فهنا ماكو غطاء نباتي في سبتمبر 2004، في حين الغطاء النباتي أكثر بال 2005. ولذلك نشوف هنا العواصف الترابية بالصورة الجوة اللي مكتوبة شلترينج، العواصف الترابية والرملية أكثر كثيفة، في حين بالصورة اللي بجانبها ماكو. ليش؟ لأنه الغطاء النباتي كثير. هذه صورة من الحقل اللي زميلي من جامعة نورثرن أريزونا. مثل ما تشوفون الكاميرا مخليها هنا على الجبل حتى تاخذ صور للعواصف الرملية. هذا جهاز اسمه سنسيت يعطيك ايش قد عدد الجزيئات اللي تضرب البليت. فمن تصير عاصفة رملية والرمال تتحرك والجزيئات الأخرى تتحرك، راح تشوفون أنه هذا الجهاز يعطي ايش قد عدد البارتيكلز الجزيئات اللي تضرب البليت. فهذا السلايد الأخير اللي أنا مخليه للأخير. ليش؟ أنه الغطاء النباتي دراسته وبدقة أكثر ومن ساتلايت ذات دقيقة أكثر تعطينا أكثر وأحسن نتائج بالنسبة إلى مراقبة العواصف الرملية والترابية. بهذني السلايدين الفوق تشوفون هذني النقاط الزرق، واللي هي كانت دراير بسنة 2000. فسنة 2001 كانت أمطار أكثر، فالغطاء النباتي أكثر. فلو معتمدين بس على الرياح، بس على بيانات الإرصاد الجوية، معناها أنه هنا موجودة عواصف ترابية ورملية إذا إحنا قاعد نتنبأ. بس بالحقيقة تشوفون ماكو كل عواصف رملية ولا عواصف ترابية، والبارتيكلز اللي تضرب هذا الجهاز ما موجودة. ولذلك الفكرة مالتنا أنه نركز على الغطاء النباتي ونستخدم بيانات الإرصاد الجوي بشكل ثاني، وأيضا نستخدم الساتلايت الدقيقة اللي هي مثل لاندسات وسنتينل، واكو أيضا ساتلايت كوميرشال اللي هي تعطينا حتى نص متر. جائز نستخدمها حتى نحدد بالضبط مراكز العواصف الترابية، وبعد ما نحددها ونرسمها نقدر نروح على اللاندسات والسنتينل وغيرها. فهذا فشيء جدا مهم أنه شفناه بالحقيقة، أنه إذا نعتمد بس على الويند، بس على الرياح، بهاي السنة إذا واحد قاعد يتنبأ راح يقول أكو عواصف رملية وترابية، بس بالحقيقة ماكو. ليش؟ لأنه كانت وتير والغطاء النباتي أكثر. شكرا جزيلا. Thank you so much, Mr. Bill.
Thank you, Dr. Amir, very much for that presentation. We will stay now in the field of remote sensing, and we will transfer the screen sharing over to Gabriel Sine, who will talk to us about using remote sensing-based ET for crop, water use mapping, and drought monitoring. Gabriel? Gabriel, we can't hear you if you are speaking. We see your screen.
I am amazed I stayed within time.
Saud, I do not have control to unmute Gabriel.
Oh, let me contact Engineer Hamdia.
Hello. Now I think I'm on mute now.
I hear you. Yes, we hear you now.
Okay, perfect. All right, I think my video is still off, but that's okay. Because do you see it in full screen now? My talk?
We see your screen. Yes, it is not in presentation mode though.
How about now?
Very good.
Excellent.
If you go to the lower left corner, do you see the video? Maybe that one is crossed.
Yes, I tried to, but yeah, it's not letting me. So I'll just keep on
You
talking.
keep going. I will talk to Engineer Hamdi and see if they can do something.
Okay, sounds good. Yeah, thank you very much, Mr. Chairman. So I got a lot of slides, so I'll keep going. So title is, well, I am Gabriel Sanai with the USGS. I'm located in Fort Collins, Colorado. So I'll be talking about how we use remote sensing data for water use mapping and drought monitoring. I'm collaborating with my colleagues from AROS, USGS AROS, and this is a general outline of my talk. I'll spend a lot of time showing how we use satellite data for drought monitoring applications globally, but I will have an example over Iraq and its surrounding region. And if time is available, we will go into the modeling principles and some other applications. But these are the most important slides I want to show you. So this is from AROS, Earth Resource Observation Science, where I work with Dr. Saud Amir, who hired me a long time ago. So that's in South Dakota. I'm located in Colorado. And the center, AROS Center, is where we host the Landsat satellite that Dr. Saud mentioned earlier. So we have now Landsat 8, Landsat 9 is coming. That's where really AROS is all about. So satellite data, I call this as a great equalizer because there is a uniform quality of data available for anywhere in the world. So the quality of data over the US, over Iraq, over Africa is practically the same. And it's available for environmental monitoring, equally available for everybody with the same quality. So we use satellite data to do a lot of global monitoring. You might have heard about the famine early warning system network. The remote sensing component of this project is with USGS AROS. We monitor vegetation using a vegetation index from a satellite. We monitor weather data like precipitation, satellite-derived rainfall data. For hydrologic parameters like soil moisture and evapotranspiration, the one I'm talking about, that's also satellite-derived. There are a lot of, we combine this with field information like grains and prices, and to come up with a hazard warning system every week. So this is an example application of how we use convergence of evidence in the FuseNet program. So these are independent data sources. So we use satellite-derived rainfall. This is, for example, in Southern Africa and in Botswana in here. So it shows below normal for the 10-day period in here in 2018. And we use NDVI, Normalized Difference Vegetation Index, completely derived independently. And the anomaly shows also below normal in here. And we use another independently derived ET data from the thermal. So this is from the optical, this is from the thermal component. And we derive evapotranspiration that shows us below normal. So when these three independent data point to the same below normal condition, we kind of develop a kind of a hazard map every week with our collaborators, and we distribute this to USAID, to the State Department, and partner organizations like FAO, WFP have access to this product. So this is a weekly product produced using independently produced data. It's an example of a global application of the ET derived from the SSEB model or CBAP model from AROS is something like this. And we have this operationally available since 2003. So for a growing season, for example, in the Northern Hemisphere, it shows drought in 2009, July, somewhere in a large part of Russia. And if we're monitoring Southern Hemisphere, then we look at the kind of the winter months in the north. but it's really the summer, the growing season in the south. So the actual product is this. This is actuality in absolute magnitude. You can see that where there's a lot of radiation and a lot of rainfall, evapotranspiration is higher. That's really the source of pretty much, energy cycling and over the globe. As you go north and south, lower latitudes and higher latitudes, energy is limited, so the amount of evapotranspiration is much lower. But this is very hard to make sense of it by itself. So we look at anomalies. So how this model product is different from the average condition. So this is, for example, 2018. Generally, the US is above normal, so which means good rainfall conditions in much of Africa. But part of Kazakhstan in here is below normal condition. And this is 2012. If you remember, there was a major drought, much of the US, also much of Europe. And so that's also captured. This is a 1 kilometer product every 10 days. It's operationally produced. And this is 2019, again, and a major drought in part of Russia. And if you look at the reports in here, there's a lot of news reports how dry, the regions around the Lena rivers are. So now, how is this applying for Iraq? So I'm going to show you some products, how this product behaves in Iraq. So this is our ET distribution around Iraq and the surrounding regions. So again, this is a 1 kilometer product derived from models using CBAB model from Usgs Aeros. As you can see, the rain-fed system shows green. So green is where there is ET, and 0 is pretty much no ET, no vegetation, the desert. So our focus is more in irrigated areas in here and more of a rain-fed systems in here. So this is the average condition of evapotranspiration distribution in Iraq. This is Baghdad in here. And so we can take a look if you focus around Baghdad area, and we can, of course, get more details. So again, this product is freely available. You can download this from the website. So now let's look at individual years. When you look at individual years, again, this is annual total ET, evapotranspiration over Iraq, but you can see difference like 2011 versus 2017. For the same location, 2011 seems like a lot of evapotranspiration or good vegetation, maybe a lot of irrigation, but 2017 was much lower. Again, this is absolute magnitude, hard to interpret, so we converted this into anomalies. How does this convert to the average as a percent of the median? So what I noticed is just a lot of years from 2009, just we looked at the last few years, 12 years, is just okay. And then starts 2014, much of Iraq is showing below normal condition. So as if there's almost a major reduction in irrigation. 14, 15, 16, 17, and then 18 was okay, 19. And then those in the room who are looking at this data, you would be witnesses. Was there something happening for the 4 years in a row from 2014 to 2017? Was there any policy change, or there was a water distribution change from upstream? And then there were 2 years of okay, and 2020, again, it went down. So when you look at that, that's just annual total. And when you look at also month by month, and you can see that which month is really the one where vegetation is active. As you can see, May is actually the one that peaks with evapotranspiration, especially over the rain-fed areas. That's where really most of ET is happening, is in May. But of course, in irrigated areas, you can have ETs throughout the year as long as you have enough water, mostly. So now we want to look at how the ET behaves between irrigated areas versus rain-fed areas. So we downloaded just a coarse map in here of crop layers. The yellow is just general cropland, a rain-fed system, but I'm surprised to find rain-fed system. This could be a misclassification, but the green areas are supposed to be irrigated. Now I'm going to show you evapotranspiration, which is how much the plants are transpiring water, and how this is behaving over the years. So what you see in here is the one on top is over irrigated areas, and this is rain-fed areas, and this is just the background desert. As you would expect, irrigated areas will have more evapotranspiration, they use more water. Rain-fed areas, lower water, and the background, this is pretty much the rainfall background. So just, it's hard to make sense of this. Is very low ET, probably within the margin of error of the model. So our interest is really, can we monitor the year-to-year variability of water used by crops. So as I showed you on the map, from 2014, 15, 16, 17, there was a reduction in evapotranspiration generally. So also, what's interestingly, the rainfed system also reduces, so there was really rainfall reduction, but the irrigated areas actually are reducing more, which means there was really a supply problem. So the irrigated areas were not getting enough water. So how is the seasonality of this? Again, we looked at the same irrigated crops, irrigated areas, and rain-fed areas, and non-crop lands. Well, as I said earlier in the map, May is month 5 in here. Both the irrigated and the rain-fed areas, they peak their evapotranspiration in May, and then it quickly comes down for rainfall, the rain-fed system. But for irrigated system, it really ramps up in May, and then holds steady, high evapotranspiration in May, June, July, and then in August and September, it comes down. Probably harvest is happening somewhere in September and October for much of the irrigated areas. So this is kind of data you can download easily and just make a lot of analysis. All right, now you're gonna be wondering, where do you get the data? Well, this is our famine early warning system data from USGS. You can go to this data, this website, you can download the data, and you can select by region. You can download the whole of the world, and you can select the year and the month, and data is available for download. So as I promised, if we have some time, I'll go through the principle of the physics of how we model this. Again, this is just 2 slides. So the schematic of the model, we use weather data, and we use satellite data. From the satellite data, the land surface temperature, the temperature of the skin of the earth or the crop canopy is the most important information. So we use that data to come up with an ET fraction, and we use the weather data, what we call it the potentiality. If water was not limited, how much would be the evapotranspiration? So we combine the weather data, the potential, with the actual limitation and what we call it a 2-parameter model, and estimate ET fraction and actual ET. In short, this is how the model works. 50% of the model is this. If the landscape is well irrigated, it will be much cooler because of evaporative cooling. And if there is a lot of bare areas, young crops, there is no evaporative cooling, and the land surface will be much warmer. So this is a Kelvin by mistake, sorry. So this is, for example, the difference between a bare ground and a well irrigated area could be as high as 20 degrees centigrade or 20 Kelvin. So there's that evaporative cooling is the most important driver in modeling evapotranspiration. So where do we get the data to model this? Well, we use a lot of global data sets to model this. There's a lot of global data available. For example, reference CT can be available from GDAS Global Data Assimilation System. Different sources. We can also use station data. But for the satellite data, we use MODIS or Landsat. If we're interested in field scale modeling, we use Landsat. For regional scale analysis, we use MODIS. So with the Iraq Ministry of Water in Iraq, we are working with Dr. Ziad Mohammed and Engineer Hamdia to implement this model using both Landsat and MODIS, and through the kind of partnership that Dr. Saweed Amir talked about. The data is freely available. This is, for example, an example of MODIS covering the whole world. And this is what we call the Penman-Montes, a potentiality that's also available globally. You can download it from our website. This is just for example, a 1 day for July 5th, 2020, the potentiality when water is not limited, as you can see in here, Iraq shows really deep, brown red, which means high evapotranspiration. So regions like Iraq will be consuming a lot of water. For irrigated crops in Iraq will use a lot more water than somewhere in other places, like obviously in Europe, where the atmospheric demand is much lower, almost half. So there are applications using Landsat. How am I doing with time, Mr. Chairman?
Yeah, 1 minute, Gabriel.
Okay. Yeah. So just really quickly showing, we can also do this with Landsat. This is, for example, Landsat based and MODIS based. The difference is, which one should we use? Well, if we are interested in really small understanding the field water use, we can use Landsat. if we are really interested in just basin scale analysis, we can use models. So at a certain scale, they should give comparable results at the basin scale. But if you want to analyze really in a farmer's field, we want to encourage you to use Landsat. We validate the model in the US as well. There are flex towers. I don't know how many flex towers you have, what they call them, eddy covariance in the US. But we validated the model in different parts of the US. There are some good relationship between model and field observations. And we can apply this in combination with water balance, water budget. So for example, a rainfall distribution map in upper Mississippi River in the US, you can see the fine detail we get about evapotranspiration map from a satellite, because satellite gives you that 1 kilometer, in this case, 1 kilometer resolution that you cannot get for precipitation. And evapotranspiration, of course, is a function of soils and land covers, which means it captures a lot more fine detail information about the hydrologic processes. Yeah, once you have the evapotranspiration, it just helps you understand the whole hydrologic water budget. So ET and in green you have got the runoff and rainfall, excuse me, in blue. So these are my final remarks. Again, the ET data is available for download, and for drought monitoring, you can use it as is. For water budget applications, it requires a one-time calibration. I will stop right here if you have any questions. Sorry, I seem to have rushed a little bit. Thank you.
Thank you very much, Gabriel, for the excellent presentation about it. This is an excellent product used worldwide, and Gabriel's skills are in great demand within the USGS water community to evaluate water availability. We'll transition next to Tom Mack, and Tom will speak to us about a novel geophysical approach to assess sediment thickness. Tom and Gabriel, can you relinquish control of your screen so Tom can take control?
Salam alaikum. Thank you for having me at this important conference. I wish I could be there in person. Let's see if I can get my screen. There we go. Okay. I'm Tom Mack from the U.S. Geological Survey.
Tom, do you want to move to presentation mode there?
Oh,
Yeah,
my screen it is.
You don't have to, but
Sharing the wrong screen. Let's see. Yeah, I can't switch screens. I'm going to go with this.
Okay, sure thing.
I'd like to acknowledge my co-authors listed here, and also the USAID and the Afghanistan Ministry of Mines and Petroleum who are funding this work. I'd also like to acknowledge the USGS branch or hydrogeophysics branch. Our next speaker is actually the chief of that branch, and he has personally taught me the techniques that I'm presenting today. This is the issue that we're talking about. Here we have, this is a basin in eastern Afghanistan. We can see it's a very large basin. There's actually a drill rig in the bottom right corner down here. We need to know the sediment thickness in this basin, which is critical for determining the water storage in this basin. We can only drill in a few locations. Drilling time is very expensive, and bringing a drill rig to this remote location is even more expensive. So we want to optimize where we drill throughout this basin. So I'll show you, I'll talk briefly about the theory, show you the equipment, and then talk about the surveys that we have done in 2 basins in Afghanistan. Very briefly, the passive seismic method. With this method, what's unique is that there's no need for a generated seismic sound source. We use ambient noise, just background noise. The equipment, the method requires a contrast in acoustic impedance, and you can think of that as looking from unconsolidated sediment to a consolidated or hard rock. You need a contrast like that in the profile that you're looking at. The equipment has a very small footprint. I'll show you that in a minute. And we record for about 30 minutes. The method is effective from a few meters to, I've used it to 1,000 meters. The seismograph measures 2 horizontal and 1 vertical noise component, and the sediment thickness is directly related to the resonant frequency of the ratio of that horizontal to vertical noise component. This method is often called H/V for that reason. When we're first looking at a region, we might use empirically derived coefficients from another region, but ideally we would want coefficients derived for the area that we're looking at. And I can refer you to actually our next speaker. He's the person that has published more on the methods. Here's a field form, but here is the actual equipment in the bottom of the screen. So that shows you how small and portable this is. That unit is less than a kilogram. We carry it in this case, and we might ship it in a cooler like this. So highly portable, and it only requires that space right there to collect a measurement. Most other equipment requires, other geophysical surveys require a large land area. Here's an example of the seismic record that we collect, where this is over almost 20 minutes. We see the different components of the noise, the horizontal and the vertical here. When we process this seismic record, we end up with a graph like this, where we're looking at the horizontal over vertical amplitude on the y-axis, and on the x-axis here, we have the resonant frequency. In this graph, we've superimposed 3 different locations, and the sediment thickness at these 3 locations are 300 meters, 20 meters, and 4 meters. So you can see that the resonant frequency at these 3 different sites shifts, and this is what we use to look at any new site. In this example, I'll be showing mostly data from this site in eastern Afghanistan, and then there's a report that describes this in more detail, and that was the first picture I showed. We use information from there, and then we applied it more recently at this basin in western Afghanistan. Oops. Here is the basin in eastern Afghanistan. There was, before the drilling was done in this basin, there was also a gravity survey was done, and that's more typically done in large basins. But to do a gravity survey, they first needed a digital elevation survey. So these are the points where digital elevation was collected, and then gravity was collected in between these. These points are 1 kilometer apart. So this is a lot of field work that went into just the other geophysical survey. And that required over 3 weeks of work to do the digital elevation and the gravity. And here you can see this is a picture of the collecting digital elevation data. To do any field work in this setting required a security team. And when the crew that's camped out there doing all this work, they require a base camp with security. So these things become very expensive. This picture on the left shows the gravity survey. We collected seismic data at these points shown on the map. I won't show all the data. And drilling came in afterwards, and these are the borehole thicknesses. When we looked at the gravity process gravity data and the seismic data, we found that they showed very similar results. We saw the same pattern with both surveys. However, ideally, when we do this work, we like to develop the coefficients for that particular region. Unfortunately, with this data, these boreholes did not reach bedrock. However, at these 3 boreholes, looking at the other geophysical data, we could tell that they were probably very close to bedrock. So we used these 3 points to come up with a curve for this region. It's an approximation. If we look at these 3 points, if we blow that up, the issue we have is we can see that there were deeper, some of the data showed that there were deeper, thicker sediments in that basin. However, our curve would not be accurate at these points. So we found another basin with almost identical conditions as this, a basin in the western US, where sediment thickness was 1,000 meters, and we had boreholes to confirm that. We collected seismic data there, and so we were able to put more data points on this curve. So the first basin I showed you, the eastern basin, had data points all down in here, less than 100 meters to up to 250 meters. However, the western basin, where we went to next, we could, from the seismic data alone that we collected, we could tell that the sediment thickness was more than 500 to 800 meters thick. So that western basin, from this very preliminary work, looks to be a very good target for drilling. There are problems that can occur with this technique, and one that came up for us most often was in these basins in the afternoons particularly, there were very high winds. We can counter that by covering the equipment. Normally we wouldn't sit on that bucket, we would put it over the equipment. We also had a problem with loose soil, where the equipment, here we can see the bottom of the equipment and spikes that go into the ground. It did not couple well with the ground surface. We can counteract that also by removing some of that surface sediment. In one of the basins, I could not go to this basin, we could not go there. So the driller's assistants actually collected the field data. They were obviously not highly trained, and so, but still they were able to do this survey. So it's something that can be done quite easily. So in summary, this technique is a very good reconnaissance tool to determine if a site is worth further evaluation. It's fast. Each data point is collected in about 30 minutes. In the Eastern Basin, we collected 80 data points over 8 days, and that was with a very inexperienced crew. The gravity in comparison took over 21 days to collect that data, and more time to do the digital elevation survey that was also needed. In the Western Basin that we went to next, we collected 18 data points over 2 days. And this data is processed with no other supporting data other than a basic understanding of the geology of that region. The equipment is inexpensive. One unit, the unit that I showed, costs less than $10,000 US. That is, of course, a lot of money, but very little compared to other geophysical setups that may cost up to $100,000, such as time domain or refraction. There are limitations. The equipment may not be effective if you have a semi-consolidated rock sediment over bedrock, or a thick weathered surface on top of the rock. In those cases, you don't have that sharp contrast in acoustic impedance that you need. Other issues I talked about, loose sediment or wind, these are also problems which we can counter. Shakran, thank you. That's my talk.
Thank you very much, Tom. Under the right conditions, these simple measurements and combined with some clever processing yields powerful results for aquifer thickness and water availability. Thanks for sharing that with the group, and contact Tom with questions, or we'll have time at the end here for those questions. We'll transition now to another hydrogeophysical method, and John Lane will present to us an electromagnetic method, a new approach. And so, Tom, can you relinquish control so John can grab control of and provide his presentation?
Okay, I think I have. John, are you able to?
Okay, we are unmuting John now. John, I think you're on now. If you can. John, can you speak?
Bill, do you want me to talk to the organizers?
I see him as unmuted on the participant list.
Yeah.
John, can you check your?
You can see.
Okay, we will. I think Wayne Belcher is on. So while we try to get John's connection worked out, we can move to the next speaker, I believe, and that is Wayne Belcher. So, and Wayne will talk to us about USGS hydrology and hydrogeology programs in Iraq. And I see Wayne is making the transition right now. And Wayne, we are seeing your screen.
Can you hear me?
Now I can hear you, yes.
Okay, wonderful. Okay. Well, I want to thank first off the organizers of the conference for letting me talk a little bit about the USGS groundwater programs in Iraq that I've been involved with for over a decade. And I would also like to acknowledge my co-authors, Dr. Saud, Dr. Lankashet, Engineer Hamdia, and Dr. Acer from the Ministry of Water Resources. And I thank you for this opportunity. The USGS has been involved with international work for decades, for over a half a century. In 1879, when we were first formed, we were mandated to classify the public lands of the United States and examine the geological structure and mineral resources of our national domain within the borders of the United States as they existed and continue to expand since 1879. But in 1962, our mandate for doing the same work was extended outside the United States. So this gives us the mandate to apply our expertise and our scientific knowledge to international work. And I put this on there because a lot of people in the United States, I often get asked this in airports, why are you, when I'm traveling, why are you going over there? And it's like, this is our mandate, and it's to share our expertise with our colleagues overseas. So the USGS water mission area with groundwater, what we've done is over the decades that we've been in existence, we've developed protocols for groundwater data collection and evaluation of new instrumentation techniques. We perform national and regional groundwater assessments. I've been involved in national and regional groundwater assessments in the state of Nevada for most of my career with the USGS over the last 20 years. We develop data repositories and sharing. These are publicly available databases. We conduct applied and theoretical groundwater research. We develop modeling and geophysical tools. Some of these you've already heard in the previous talks. And we lead water use and census activities so we can tell how much water is being used. And these are all techniques and knowledge bases of how we've done these things that can be extended to our partners overseas. The other thing we do is aquifer specific assessments of recharge, sustainable groundwater yields, changes in storage in the aquifers, saltwater intrusion, indices and trends, how much water is being used, how does drought affect water availability. We look at artificial recharge and groundwater and surface water interactions. And again, these are groundwater assessments and tools that we've developed that we can apply to our international partners. So the water resources that I've been involved for over the last decade with the International Programs Office, mainly what we've been doing is we've been assessing water resources in areas to focus on sustainable water supply development. And we mainly look at a regional scale. We're looking at inaccessible areas, either through security or location. And what we've done is working with Dr. Saud for over the last decade, we've developed a process of looking at remote sensing coupled with traditional hydrogeologic assessment, and then added on an economic assessment of the water resources that are done by our colleagues at New Mexico State University. And they'll be talking about that later in this session. So that there are 3 programs that the USGS has done in Iraq that I've been involved in. And the first one was from 2009 to 2011, and we looked at water resources for development of water resources, information, and tools in support of economic development in the western and southern deserts and the Kurdistan region of Iraq. And this was task 2 of a big project that was funded by our U.S. Department of Defense. The next project that I was involved in was with Dr. Saud. We were, the USGS was tasked for being science advisors for the ASHRI 2 study, which was funded by UNESCO and the EU. And that was from 2000, I have to hide this, from 2014 to 2017. And I had the pleasure of working with a really good team, and I'll talk more about that in a minute. And being, even though it was the USGS, it was a science advisor, I was one of the individuals that was able to oversee and advise this project. And then the latest project that I've been working on was an update to the National Water Strategy Plan, the groundwater portion of it. And that was funded by our US State Department, and worked on that from 2019 through, I guess that should be 2020, not 21. So the objectives for all of our groundwater projects was to develop a new knowledge base of groundwater resources in Iraq, and to update knowledge and capacities for sustainable management of the national groundwater resources. And with every one of these projects, we do a component of capacity building. For the specific products and models and tools that are developed or used in these projects, we train the Iraqi water professionals on how to use these projects or these products. We also provided USGS style training on techniques such as in remote sensing, monitoring networks, and data collection. And then what I've been mainly involved in is the hydrogeologic modeling. So on a personal note, I live in Las Vegas, Nevada. You can see the outline of the state overlaid on Iraq. It's about this, Iraq's a little bit bigger than the western state of Nevada where I live, but I've been able to take my expertise in arid hydrology that I've learned working in Nevada for 20 years and apply it to Iraq. It's very similar in size, and also we have, like the Tigris and Euphrates, we have a big river, the Colorado River. We rely, at least in southern Nevada where I live, we rely extensively on our water supply from that river. The Las Vegas area gets about 80% of our water from the river and 20% from groundwater. And we are desert in the south, and in the northern area, it's very, very mountainous. So it's, I've enjoyed working on the geology. It's interesting to me, the hydrology, but also the people that I've met and the water professionals are excellent. So the first project I'm going to talk about was when, excuse me, when I initially got involved with the international work, was the groundwater assessment supporting economic development in priority areas in 2009 to 2011. Excuse me. I was involved in the groundwater task, which was task 2.1. And in this, we were going to train, our goals were to train Iraqis in USGS style groundwater assessments, provide a basis for a numerical model by looking at the geometry, the thickness, and the spatial extent of hydrogeologic units, develop a conceptual model of groundwater flow, and make these all quantitative so they could be input for a numerical model. And I co-led this with my colleague from another Western state, Idaho, Jim Bartolino. So task 2.1 was the groundwater assessments. And we had two areas that we were mainly working in, the Southern Desert and the Kurdish region in the north. So this shows some of the areas that we were considering, the Erbil Basin, the Shorazor Basin, Western Desert, and the Southern Basin. And we had selected these basins up in the Kurdish region, and then the southern desert. The unfortunate thing, okay, and in the hydrogeologic assessment, what we're going to do is define the hydrogeologic units, which are units that are based on the hydrogeology and have similar properties. So we can lump these together. And so rather than dealing with individual lithostratigraphic units, we want to look at the availability of water, develop a groundwater budget, and then a conceptual model that can then be used to create a numerical model that can be used for prediction or answering questions. And models can also, numerical models can also be used to integrate all your data into a holistic source where you can have your data available. That's one of the purposes, I think, of groundwater flow models, and it helps you determine where you need to investigate other areas or data gaps in your data. So our hydrogeologic study in general would define the input and output of water, the aquifer properties, and we look at potentiometric maps, either existing or we make them from water levels and wells, hydraulic properties, spring flow, evapotranspiration, any pumping in the area, recharge, and then, as I stated before, the hydrogeologic unit geometries. And all the purpose is to gather a quantitative assessment of the hydrogeology so that we can use this to make a numerical model. The unfortunate thing about this, the work was cut short, and we did not complete this, but some of this work was used in phase 2 of ASHRI, which I found satisfying rather than just having this sit around on our computers. So ASHRI 2 was approximately 2014 to 2017. And this was involved with several personnel associated in the EU. SGI and T0 were Italian companies. RTI, which I've done several projects with, are based out of Tarascon in France. And then the USGS, we were technical advisors for this project. So the methods are that we used in these projects, in this project, was a remote sensing interpretation, looking at mainly radar and how moisture can affect and attenuate the radar signature, coupling that with a traditional hydrogeologic analysis of looking at recharge and discharge areas, cross sections of the hydrogeology, pumping, recharge amounts, discharge amounts, and then all this information was taken and put into numerical models. Our study area was this, most of Iraq, except for the northern mountainous range that borders Iran, this area right in here. And it was a very large study area, 404,000 square kilometers. Our workflow that we did was we collected the remote sensing data, interpreted using a proprietary radar interpretations. We mapped the extent of the aquifers and recharge and discharge amounts and area, and developed a conceptual model. The hydrogeology, we looked at cross sections, pumping, recharge, discharge, and the hydraulic properties, in a three-dimensional model of the hydrogeologic units, which we call the hydrogeologic framework model, or HFM, which is a three-dimensional volumetric model of the hydrogeology. And all this information was put into numerical models in selected priority areas. And these priority areas were in the north in the Kurdish region, the Western Desert, and the Southern Desert. And this report was published, and this is the ASHRI 2 report, and it is very long, but it is full of a wealth of information. So, and this is an example of some results. Here on the left, we have a compilation of wells for both phase 1 and phase 2. And this is in the middle here over to next figure to the right. This is a figure of springs and their location. This is an interpretive product here showing recharge areas throughout the study area. And this is an example of one of the really nice cross sections that were done that helped us define the subsurface geology and hydrogeology. So those are examples of some of the products that came out of the ASHRAE 2 report work. So in 2019 to 2020, I worked with 2 Iraqi nationals, that would be Engineer Hamdia and Dr. Acer, and we integrated the results from the National Water Management Plan with these earlier studies and new data that have been collected since ASHRAE 2 had been completed. And so we initially worked on remotely by assigned reading of the Water Management Plan and the ASHRAE 2 report to see what the differences are, where we can update. And we had monthly, trying to have monthly conference calls. And then there was Engineer Hamdia and Dr. Acer came out in January and February in 2020, and we worked on producing a document. And at the end of their stay, we had produced a draft, which then we finalized in the spring of 2020 to update the groundwater knowledge that we had integrating these earlier studies. So these are some of the updates that we had. Over on the left here is a classification of groundwater suitability for agriculture based on total dissolved solids. In the middle here, this is another map showing different wells that we compiled, including new wells that were between 2000 that have been drilled since the ASHRAE 2 study had been completed. And then over on the right here is a new using a compilation of data, the existing data and new data that have been collected since ASHRAE 2 to produce an electrical conductivity map. And these were all described, and these are just examples. There were many more things that had been done in this document. So what we have had a long-term collaboration with the Iraqi water professionals and the U.S. Geological Survey. We've been working with water resource professionals for well over a decade, and we've been engaged with the USGS and the various water ministries and the agricultural ministries and the geologic ministries. And what we envision is in the future that as more projects are done and more work is done, that we can be involved in. And this is a continuous update of the National Water Strategy Plan with new data, ASHRAE 2 and others, as we move forward in time and more data and information is getting published and getting out there. One of the things that we would like to do is to take all this information and produce water budgets with numerical models to integrate these data that we talked about earlier. And that would be done in collaboration with the Iraqi water professionals. And we would be using public domain software because it is difficult. A lot of times this software is very expensive. And so we're trying to think of public domain options that will limit the cost for our partners. And with that, I am done. So I'm going to stop sharing. And
okay, thank you very much, Wayne. We appreciate the presentation. We're still working on John Lane's issues with John Lane's connection. And so we will we'll transition into the modeling portion of the presentations today. And I will introduce David Said, who will talk to us about a tool called Sparrow. David? And I am asking to unmute you. I think you're okay now, Dave. So
Can
yeah.
you hear me and can you see my slides?
Yes and yes.
Perfect. Thank you, Mr. Chairman. My name is David Said. I'm a hydrologist with the USGS, and I'm located in Middleton, Wisconsin. I work with a team of USGS scientists to develop large-scale water quality models for different regions of the United States. The regions representing the most recent models are shown on this map. For each of these regions, we developed models to simulate long-term average stream flow, nitrogen, phosphorus, and suspended sediment load using the Sparrow watershed modeling software. The examples I'll show today are geared toward the nutrient models with some specific examples for nitrogen. Sparrow models can be developed for constituents of interest beyond those shown here, and models have been developed at various locations throughout the world. If there is interest, support, and available data, this is a tool that could be applied in Iraq. During this presentation, I'll describe what a Sparrow model is, what type of input is needed for Sparrow models, and the types of useful output that you can get from Sparrow models. So Sparrow is an acronym. It stands for Spatially Referenced Regression on Watershed Attributes. It is a mass balance model that utilizes a hybrid statistical mechanistic approach, and it uses nonlinear least squares regressions to develop a relationship between monitored loads and spatial data. The spatial data represents sources for the constituent of interest, watershed characteristics, and in-stream decay functions. In addition to the recently developed regional models, national models in the United States have also been developed for nutrients, total dissolved solids, and total organic carbon. Models for other constituents and other locations around the world have also been developed. The Canadian, New Zealand, and Spanish models have all focused on total nitrogen and total phosphorus. The Wujiang River model in China focused on ammonium nitrogen. The Ishikari River model in Japan focused on suspended sediment, and the Grande River in Brazil focused on total nitrogen. Output from Sparrow models can be used for a variety of needs. The models can be used to extrapolate from monitored areas to unmonitored areas. You can use the model to identify areas of high load, high yield, and high concentrations, which we often refer to as hot spots on the landscape. You can also use it to identify sources contributing to constituent loads. And because of its statistical nature, you can get confidence limits on model coefficients and the load estimates. With the Sparrow model, all the results are scalable up from the smallest catchment to larger watersheds and even larger political areas. And you can use the model for scenario testing. You can look at load reduction strategies to achieve a water quality criteria or evaluate impacts of future climate or land use change. The two bullets highlighted here are some of the most useful features of a Sparrow model. Information describing high loading areas and the sources contributing to those high loads is often needed by resource managers to make decisions about how to implement stream water quality improvement strategies. This slide shows examples of the type of problems that a Sparrow model can help to address. Each year, a large hypoxic zone develops in the Gulf of Mexico, just off the southern coast of the United States. Hypoxic zones are areas of low dissolved oxygen in the water, commonly near the bottom of the water column. It's caused by the decay of an overgrowth of algae that is fueled by excess nutrients. The Gulf of Mexico hypoxic zone can cover an area larger than 20,000 square kilometers and has a huge impact on the fishing economy there. Research has shown that nitrogen and phosphorus delivery from the Mississippi River watershed are the main drivers in the development of the Gulf of Mexico hypoxic zone. A Gulf Hypoxia Task Force has been set up to evaluate this problem. The task force has recommended a 45% reduction in nitrogen and phosphorus load from the Mississippi River watershed to reduce the size of the hypoxic zone. In order to do this, resource managers need to know two things. They need to know where the nutrients are coming from on the landscape. These are the hot spots that I referred to earlier, and they also need to know what are the sources. Sparrow models are well suited to answer these questions. Later on in this presentation, I'll show some examples that address these specific questions. As previously noted, Sparrow allows you to extrapolate from a relatively small number of monitoring sites to a relatively large number of unmonitored reaches. But how does it work? The model develops the relationship between monitored loads and spatial data. Spatial data includes sources, land to water delivery variables, and in-stream processes. All of this information is indexed to a routed digital stream network. Once everything is indexed, the model is calibrated using nonlinear least squares regressions. In this regression, the monitored loads are the Y variable and the spatial data are the X or independent variables. Once calibrated, the model can predict long-term mean annual loads at all stream reaches and can keep track of the origin and fate of constituents throughout the stream network. And because of its statistical structure, Sparrow can provide information about uncertainties in the model predictions. So as you can see here, lots of information is needed to build a Sparrow model, and the next few slides will describe this information in more detail. The backbone of the Sparrow model is a routed digital stream network. For the regional models, we used a data set called NHD+. A link to this data set is shown at the bottom. Monitored loads and spatial data are indexed to this network. From-to connectivity and diversion fraction attributes built into this digital network allow spatial data to be accumulated down the network. This connectivity also allows source and delivery information to be tracked throughout. The NHD+ data set has a corresponding set of watershed catchments. The typical catchment size is about 2 to 3 square kilometers, so they're quite small. All spatial data used in the Sparrow models are processed down to the catchment level. Sparrow models need source data that describe the constituent of interest. These models can be built using simple area-based sources like land use and land cover. However, more spatially variable and detailed sources like fertilizer, manure, atmospheric deposition, and wastewater discharge inputs can improve the model results. Many of the spatial data sets used in the Sparrow model require extensive pre-processing to allocate information down to the catchment level. Here's an example of how we estimated fertilizer input at the catchment level. To do this, we used a regression model that estimated catchment level fertilizer use from state and county level fertilizer sales, crop information, and climate and manure data. This process allowed us to extrapolate the coarse state and county level data down to the finer catchment scale. Land to water variables typically represent climate and watershed characteristics that enhance or inhibit the delivery of sources from the land to the stream. Commonly used land to water variables in Sparrow models include climate variables like temperature, precipitation, and runoff, and watershed characteristics like slope, soils, geology, and land management practices. In-stream and in-reservoir decay functions remove sources through various processes like settling, storage, and denitrification. These functions are typically defined by stream reach time of travel and reservoir residence time, which are calculated from readily available stream flow, stream velocity, and reservoir area attributes. Sparrow models are calibrated against monitored loads. To estimate loads, you need monitored stream flow and monitored concentration data. The data and method used to generate the loads used for the regional models can be found through the link shown here at the bottom. Many monitoring sites representing a wide range of source and watershed conditions are needed to calibrate Sparrow models. Loads can be determined using a variety of methods. For the recent regional Sparrow models, we used two methods, one referred to as the Beal ratio estimator and another known as a 5-parameter regression method. Once the Sparrow model is calibrated, you can use the model output to get load, yield, concentration, and source share estimates at all reaches in the model area. The next few slides will show some examples of Sparrow model output for the Mississippi River for total nitrogen. This goes along with the Gulf hypoxia example I described earlier. With this output, we can identify where much of the load is coming from on the landscape and what are the main sources of that load. Model results from each of the regional Sparrow models are readily available through online mapping tools. Here I'm showing results from the Midwest Sparrow model online tool, and the link to this mapper is shown at the bottom. These online tools allow you to easily explore model results from multiple models, and you can also download model results to your computer for additional analysis. These tools allow the user to explore output from the various models. Here we are selecting the total nitrogen model. The tool also allows you to choose an area of interest that can include the entire model area or a subset of the area representing various scales of watersheds or political boundaries. Here we have selected the Mississippi River watershed. You can also use this online tool to display results at the catchment level or aggregate it up to various watershed or political boundary scales. Here we're showing the catchment level results. And finally, you can also use this tool to select which metric you want to display on the map. You can display load, yield, or concentration. Here we're showing incremental yield, which represents the load per unit area of catchment. Darker colors represent higher yields. With this information, you can easily see which areas are contributing a larger portion of the nitrogen load that is delivered to the Gulf of Mexico. The area circled in yellow here is the area of highest yield and also the area of highest loading. This area is dominated by agriculture, but also includes some of the largest cities in the United States, including the city of Chicago. Agricultural land and cities can both contribute significant amount of nitrogen to streams, but the sources can be quite different. Here we're using the online tool to show nitrogen yield aggregated to a larger watershed scale. This is something we call 8-digit hydrologic units. These units show the results in a little bit coarser scale, but you can still see the hot spots in dark green. If you click on an area, you'll get a bar chart showing the sources that are contributing to the nitrogen load in that stream. Here I've clicked on an area in the state of Iowa. This area is dominated by intense agricultural land use. The sources shown in the graph reflect this. The dominant sources contributing to nitrogen load in the stream include fertilizer, manure, and nitrogen fixing crops. Clicking on the map near the city of Chicago, you'll see sources representing an area that is highly urbanized. The dominant source for nitrogen in streams in this area is municipal wastewater discharge. If we want to target load reduction strategies by political areas, for example, states, we can also do that with Sparrow models. Here we're using the online tool to show loads aggregated by state. The states colored in dark green are contributing the largest loads to streams in the area. This graph shows the sources contributing to the nitrogen load in streams for the top 10 states. These states are also labeled on the map. As you can see, the states of Iowa and Illinois are contributing the largest nitrogen loads to streams in the Mississippi River watershed. The amount of nitrogen from each source varies by state. This type of information is useful for helping states to explore various load reduction strategies, so different states may need different strategies. For example, Illinois may need to put some effort into reducing nitrogen load from municipal wastewater, which is the red part of the bar on this graph. However, Iowa would not get much improvement by going after that same source. As you can see, there's just a very thin sliver of red representing nitrogen from wastewater discharge. This slide and the previous slide show good examples of using Sparrow model results to get at the information needed before load reduction strategies can be implemented. With this information, load reduction strategies can be formulated for specific watershed or political boundary areas. Resource managers can use this information to target efforts to reduce nitrogen delivery to streams throughout the Mississippi River watershed, which will reduce nitrogen delivery to the Gulf of Mexico. This is just one example of how Sparrow models can provide useful information. This is my last slide, but before I finish, I want to mention that Sparrow software is currently available in 2 versions, a SAS version and an R version. Links to both the versions are shown here. If you want more information about Sparrow modeling, please see the USGS Sparrow webpage at the link shown here. And if you do not find the information you're looking for at these links, you can also reach out to me at the email address shown at the bottom. Thank you very much.
Thank you very much, David, for that nice summary of Sparrow, a USGS modeling tool for surface water. And David's example of nutrients was an excellent one. Also available to look at suspended sediment. the load, yield, and concentration of suspended sediment in streams. We'll now transition to a different part of the world. Our colleague Matthew Anderson will present some modeling tools that include decision support. And so Matthew, I will transition to you. I've asked to unmute you as well. And Dave,
can you hear me?
Could, we can hear you now. Yes. Excellent.
And I can share, can I share my screen?
You may share your screen. Yes, Dave. Dave has relinquished. Thank you, Matthew. We see your screen now in presentation mode. Thank you. Take it away.
Salam alaikum. I'm very grateful to be with you today. Thank you so much for coming in on a Saturday and staying late. I hope you and your families are well. I wish to show you today an example from Southeast Asia where we are building a model. This is especially useful for combining different kinds of resources. I think this is a model that could be useful for the Iraqi natural resources and social resources. The name of our model is NextView. This refers to our interest in trying to improve our vision or our view at the nexus of food, energy, and water, very important, very complicated resource relationships in Southeast Asia. We have benefited greatly from the support of the US Department of State. We have a number of excellent university colleagues, both in the United States and in the region. Arizona State University, Can Tho University in Vietnam, and the Institute of Technology in Cambodia. I'm going to talk to you about some of the models that we are working on, but this is not all of them. Don't have enough time to talk about all of them today. First, I will speak about our use of the ModFlow groundwater model in Southeast Asia. We will talk a little bit about our efforts to study socioeconomic vulnerability, and then how do we link those resources together using the decision theater of Arizona State University. So let me begin with the groundwater model. We are using ModFlow. This is a USGS open source model product. It's available to everyone around the world. I've been applying it to this region here, the alluvial soils of lower Cambodia from the Tonle Sap Great Lake through Vietnam to the sea, what the Vietnamese call the East Sea. It's a numerical groundwater flow model. This is, has a lot of similarities to what Dr. Wayne was describing earlier, where we try to understand what we need the model for, which questions will we be asking. We decide on important processes that occur there, define our hydrogeologic setting, what is the relationship of the aquifers and the aquatards and the substrate, and look at important processes that occur there. Define how water moves through the system in space and in time. Again, taking into consideration those hydrogeologic properties and what stresses we expect the system to exhibit. And then start to look at how we expect it to behave in the future in locations and over time. Very importantly, giving us an opportunity to conduct future simulations. This is a close-up then of our study area on the frontier, the boundary area. The use of groundwater across the transboundary region is of great importance to these small countries and to international interests. Here's the international boundary between Cambodia and Vietnam. You can see that that kind of bisects part of our model. We have taken into account the hydrologic basins that include the capital city of Phnom Penh in Cambodia, down through major cities in the north of the Delta of Vietnam of Long Xuyen and Cao Lang. These are 2.2 square kilometer grids, which interdigitate with other data sets in the region. I will also point out that here's the main stem Mekong River to the east, flowing through our study area, and then that splits and creates one of the first distributaries of the Mekong, the Basak River to the west. So here's a overview of the conceptual model and the components that we how we conceive of the system, how we describe the system. We are anticipating uniform recharge and evapotranspiration in the system at this time. We expect, we input inflow and outflow of the groundwater into this model and show some interaction with streams. We are also developing data on water use at the provincial level and hope to take it down to even smaller levels of use in the future. So as I said, one of the most important reasons for conducting this model are to be able to predict what will happen with changes to the system, trying to have a very dynamic look at what the system, how we can expect changes to affect the system. We applied a scenario that I'll show you today where we implemented a warmer and drier climate on the system, applied those changes to the model, and then tried to assess whether we can observe groundwater and surface water interactions in that changed scenario. And it turns out that the model is successful at this. So here is a comparison of the water levels that we understand today. As I say, this is a work in progress. We are still gathering more data. And you can see that when we implement that change to the system does not behave uniformly. We see a great deal of difference from areas in the northwest part of our study area where groundwater might be expected to drop very dramatically, perhaps 10 meters, perhaps up to 20 meters in some areas. We can expect drops in groundwater with that warmer, drier climate. And you can see that in the Vietnamese section of the study area, we do not see those dramatic drops in groundwater. So this illustrates the importance of looking at the international transboundary water relationships, groundwater relationships. If there are changes to the system, the two countries would not be expected to see these changes impact them uniformly, and therefore there is great potential for conflict. We also made some changes to look at how the two different rivers behave. This is, as I mentioned before, this is the Mekong main stem flowing out of Cambodia into Vietnam. This is where the distributary, the Basak River, breaks off at Phnom Penh and flows south of the river on the west. And again, you can see that there is a difference in rivers. The system does not behave uniformly. When we look at changes to the system, we expect that most of the drop in flows will occur in the upper portion of the Mekong River, not so much downstream. We expect to see fewer changes in the Basak River with these kinds of changes. So a greater change in the loss rate for the Mekong compared to the Tonle Basak, and greater changes upstream. So again, changes ununiformly, more affecting Cambodia than Vietnam. We did find then that the model allows us to assess the linkages between groundwater and surface water. And we are continuing to work in many areas on improving this model, but this is kind of our state of our progress to date. We are very interested in being able to link this model, and many of models, as I say, we're working on a few of them. Today, I want to talk about our efforts to link it to socioeconomic vulnerability. That is, how do changes to water affect people? Resilience is a very important component for people around the world in both developed and in developing countries for being able to maintain their livelihoods, maintain their lives in the face of changes, whether they are changes caused by development, and you see a lot of development going on back here in downtown Phnom Penh, or are those changes the sort coming from climate change? We think that resilience, and this is borne out in the scientific literature, resilience could be described as being made up of two components: vulnerability to change and the population's adaptive capacity. And these are all metrics that we can measure and build a vulnerability and resilience model that we can interdigitate with other models. Vulnerability is further described as being consisting of exposure to changes in freshwater availability. Consists of sensitivity. How dependent is the population on fresh water? And I'll talk more about that in the next slide. As you see here, adaptive capacity has a number of components. I'll talk more about these. What assets does the population have? What information and education do they have? How strong are their institutions? We can make measurements of that. How flexible is the population? And what is their degree of agency? That is, what ability do they have to speak for themselves? And as I mentioned before, sensitivity, we can further break up into the needs that we see for the humans, for livestock, and for agriculture, for water. At the moment, we do not have a lot of detailed information at the provincial and commune level in Cambodia and Vietnam. So we are using international standard data to help us build the model, and in this case, for levels of sensitivity. What are the needs for water in these different populations? The scientific literature describes components of these adaptive capacity that I just mentioned earlier. These are the kind of metrics then that we are collecting data for. For assets, for example, we're collecting information about the poverty rate. For information, we are collecting data about the literacy rate, and so on. Here are all measurements that can be made, allow us to develop metrics to build a model of resiliency and adaptability and sensitivity to changes. So you'll recognize this map from a little bit earlier in my presentation. This shows how with changes to the system, we saw changes in the availability of groundwater. This is not a real map. This is hypothetical. We are still building this map. But you can see how if we built a map of changes in social sensitivity, that map could be overlaid on this map to give us a combined assessment of how water resources would affect people. So what would be a good way to do that? How would we best combine those different models to show a resource assessment, resource sensitivity? To do so, we have partnered with the Arizona State University Decision Theater. This is a picture of the Decision Theater at the campus in Tempe, Arizona, near Phoenix, Arizona. The ASU also operates a Decision Theater in Washington, D.C., not too far from the White House, and they are in the process of building one of these theaters in Ho Chi Minh City in Vietnam. A very, very useful facility. They have powerful computer servers behind the scenes that are able to run many models, many data sets all at once, and then display the results of those models on 7 monitors around the room. The round nature of the facility allows for decision makers, government officials, stakeholders, natural resource managers to come together to be able to manipulate the models, see how changes in one resource might affect other changes in the system. Very, very useful tool. This is just a quick look at some of the tools, at some of the behind the scenes work we're doing today. We're looking at various elements and linking those together with our colleagues at the Decision Theater to be able to display that in that Decision Theater format. And now I would like to stop my show here and share another screen with you. Can you see that screen, Mr. Chairman?
I see your presentation.
Do you see the seat? You're still seeing the presentation?
Yes.
Let's see. Share. Now, do you see a different map?
We do.
This is a map of Pakistan, the Indus River. This is a different model that was developed by the Decision Theater in 2018. This gives us an idea of what we can expect from the next view model in the future. This is a measure of the depth to groundwater along the Indus River, very useful for looking at the changes to the system over time. The warm colors, the red colors, show a large depth to groundwater. The green colors show where it is shallow depth to groundwater. And the model allows us to look at different specific locations. I'm going to indicate Lahore and Faisalabad to show how that changes over time. And the model is dynamic, so it allows us to look at how, if the groundwater is used at the existing rates by the existing users, how changes to the system will occur over time. And you can see that we tell kind of an alarming story here, that in different parts of the system that depend on the Indus groundwater, that we can expect dramatic changes in the system over time if to the current uses are continued. This model is also very valuable for allowing us to look at different changes to environmental conditions, especially temperature and precipitation, and to look at different levels of use by different industries, agriculture, industrial use, and municipal use. So I have to be cognizant of my time. Have to stop there. And can I go back to that? I'm very grateful for your time today. I welcome the chance to talk about these resources with you in the future if the opportunity presents. I hope you have a good and safe day and that you are all well. Shukran.
Thank you very much, Matthew, for that fine presentation on some modeling and decision support tools associated with those models. We'll now transition to Dr. Frank Ward from New Mexico State University, and transition also to talk about an economic assessment. So Matthew, if you can give up control, and Frank can take control, and I am asking to unmute you, Frank. I think you are on now.
Okay, well, thank you very much, Bill. Let me see if I can do a screen share here. Can you folks see my screen by any chance?
We can. You are not in presentation mode yet, but we see you.
Okay.
Very good.
Okay, thank you very much. And I certainly extend all my thanks and appreciation to you, Bill, to Dr. Saud Amer, and to all conference organizers. My co-author, presenter, Dina Salman, and I were in Iraq in 2013, along with Dr. Saud, to give a little workshop in Erbil. And I remember thinking that there was no place in the world as hot as Phoenix in the month of August. And I discovered that Erbil was as hot or hotter, and but was nevertheless very impressed with the generosity and help given to us by the local Iraqi organizers. I think a lot of you have probably heard about implications of economic analysis for water resources planning in Iraq and elsewhere. I'm going to speak for a few minutes. I've got about 6 or 7 slides, and then Dr. Salman will follow up. I've got our email addresses right here. And so one of the big things that we have a need for in conducting economic analysis is a protocol. My colleague Wayne Belcher mentioned the need for protocols and groundwater assessments, and this is certainly true in economic analysis. And so I'm going to summarize a little bit about the kinds of protocols we've developed over the years in the US for water resource economic analysis. And then Dr. Salmon is going to present some results of an example of the use of optimization models to look at cost and benefits of various water resource policies that could be enacted in Iraq. So goals and means. So typically the goal of economic analysis, or cost benefit analysis, if you will, is to inform decision makers. Many of you have mentioned decision makers who are responsible for water resources planning, economic assessments. So that's the goal. We want to inform these decision makers. The means, the way it's carried out with cost benefit, is to enable us to provide lessons from history. We can look at past historical choices that were made, and we can assess their performance economically using cost and benefit. What we really like about CBA, cost benefit analysis, is that it provides us common denominators, usually some sort of a currency assessment of what our water program is producing in cost and benefits. And this helps guide us on the kinds of more efficient economic choices to make. And of course, this all complements the kinds of groundwater models that the USGS and others have developed. Those models provide the technical side, and then we use the outputs of those models to find out the economic value of existing policies, historical policies, or proposed policies using these common denominators. It's certainly another means is that it informs policy design. It doesn't make policy, of course, but it assesses policy proposals, so it informs them, and it gives you a protocol for doing that. And it, what I would call, shines brighter with scale. And by that, I mean the larger the scale of the policy debate is, it could be a little village or a city, or it could be a watershed or an entire country. And the bigger the scale is, or the more important the scale of money might be, the more important cost benefit becomes. Cost benefit keeps agencies honest. That is, each agency, each person really wants to have their own policy or their own project developed in their own neighborhood if jobs and wages are paid out. But this common denominator dimension helps keep people honest. It is democratic, that is to say, all water users are treated equally, and we care only about the total benefits and total cost, not so much the kinds of people that it accrues to. We really like cost benefit because it can be used retrospectively. That is, you can look at past outcomes and then try to learn from history to see if those outcomes were economically desirable. And you can use it prospectively. Prospectively, you can look to the future ex ante and assess the kinds of, or even design the kinds of policies you like using cost benefit. One of the very attractive features of cost benefit is that it permits the use of consistent assumptions. You have known output prices for things like crops and urban water supply. You have known input prices. You have, some of the other speakers have talked about future climate stress that can be run through it. So you can use consistent assumptions on climate change. You can look at new technology, and you can look at discount rates, the rates at which benefits and costs are affected in the future, discount the future. So cost benefit is very attractive for that, but it actually uses a fairly simple formula. So you're typically trying to find the discounted net present value for the, I would call it the PEATH water resources plan for the ELF affected community. It could be a city, it could be a nation, it could be a watershed. And the way you calculate that is you sum the benefits for each PEATH water plan, for each ELF community, for each TEATH time period, and you're going to sum all those benefits over the future life of the project or the proposal, and you're going to subtract that from that. You will subtract the cost using a similar formula, using a known discount rate, typically somewhere between 0 and maybe 5 or 6%. And then you would calculate this discounted net present value for each proposed policy that you are considering enacting or that you want to inform decision makers. So these are fairly standard formulas. And then so it accounts for the distribution of cost and benefits to whichever communities you care about. And then if you want, you can do sensitivity analysis. Wayne and some of the other colleagues have spoken about, you know, what's going to happen if you change your assumptions. And so you build these, economists build these what I call sensitivity matrices. So this enables you to calculate how the change in discounted net present value is affected for each, with maybe climate scenario, for example. It could be other scenarios, or really for any a change in any parameter, any price, any input price, any output price. So to be able to populate this sensitivity matrix to show how discounted net present value depends on all these parameters that could change for all these different, let's say, climate conditions that could change. This enables you to present your results of your economic analysis in a more consistent way. And I would say with that, I would ask Adina here in just a minute to turn over to talk about her application for Iraq. And so if you're looking at food security, we are interested, or we're applying cost benefit by assessing cost and benefits of various plans to protect food security. And I would say with that, I'm going to probably back out of this thing. And Bill, if you wouldn't mind letting, I'll stop my screen share and allow Dina to jump in. And Dina, are you able to do a screen share? And Bill, can you enable Dina to do it? Oh, thank you very much. Okay.
Thank you, Dr. Ward. So as Dr. Ward mentioned, to enhance the idea of the cost-benefit analysis, we did an Iraqi food security program assessment. So keeping in mind with the climate change, with the water shortage experienced in Iraq, what we did, we experienced different levels of water sharing rules. So first of all, what we did, the customary, which is an unwritten law, but it's commonly practiced. So when water shortage occurred, what happened is the upstream provinces or cities, they have the highest priority to use water because of their location, which is close to the mainstream, leaving the downstream cities with like less water or none. Another water sharing rule is the proportional sharing. This rule is seen, I saw it in the Ministry of Planning National Development Strategy, and it is written, but it's not commonly practiced. So this proportional sharing is about when water shortage occurred by around 10%, this shortage burden will be proportionally divided by each city. So each city will have the same 10% water shortage. The third water sharing rule is after each city or state or province, they have their water sharing rule, they will assess if they will use this water or they will lease it or trade it with another seller, which means it depends on which will give them the highest income. For the water supply scenarios, for what I chose the year of 2018 because it's the most driest year, averaged, I think, since the year of 2000. Keep in mind, Iraq received around 32 to 33 billion cubic meter for both Tigris and Euphrates. And then I just God forbidden in the future, if they have more water than the 2018, I chopped it by 75%, which will give us around 25 billion cubic meter. And also we did the analysis to see how we can increase the food security production and increase the farm income. Also, I kept in mind that I know in Iraq, grains, especially wheat, and I think maize or rice, one of them, it's heavily subsidized by the Ministry of Agriculture. And so I assumed that for the year of 2018, wheat and maize, they will have higher price when the farmers sell their products by around 150%. When the drought occurs, which is the 75% of the 2018, that will put the price of these grain products to 250%. Non-grain crops such as tomato, lettuce, and other crops, they are not subject to the food price programs or the price subsidies. Keeping in mind with all what I mentioned about the policy, about the water allocation, about the food price programs, we did what is called optimization model using GAN software. And it has been like, a lot of work, but due to the shortage in time, I couldn't mention all the methodology. So we have the results for the customary, which is the upstream priority. You may see the income is around 2 billion, while if they experience if they experiment the proportional sharing or the most efficient water, they will have higher income. Actually, this slide is for the grain production. I'm so sorry. So they will have around 25% more production if they will apply either the proportional sharing or the most efficient water shortage sharing. Also, that for both, for wheat in both Tigris and Euphrates. As you can see here, maize in the dry scenario, it's almost double the production, but only in Euphrates. I think it's due to the low income. It's approximately, it will be the same production as the customary water sharing rule. Here's the farm income. So this is how much farmers will gain if they will use, like the customary versus the proportional sharing versus the most efficient. Also, you'll see in the dry scenario, especially, the farm income, it will be much higher if they will follow the proportional sharing rules or the most efficient water sharing shortage. The economic value of additional water, that means in case, a farm or a city, they were able to get more water or like to dig new wells, or they will pump like more water, the value of each additional unit of water, it will be higher if they will follow the customary water sharing rule versus it will be around, I think, less than 1% or 0.05% for the proportional versus the most efficient water practice. And here's like with and without the price subsidy. You may see here and some increase with the price subsidy, that with keeping in mind because the government are subsidizing a lot. So the value of additional unit of water, that will be more expensive. For the conclusion, the adjustment in water allocation, which means for both the proportional sharing and the best water practice, will increase the wheat production by 25% in case the dry scenario occurs. Maize production in Tigris, as I mentioned, is almost double, while in Euphrates will remain kind of unchanged because of the low profitability. Farm income will be increased 26% in Tigris Basin and 18% with Euphrates. That when they will apply the price support program. And when they will apply the price subsidy, there will be a 3% more production rather than without the price subsidy. The scope and the limits of this work, we haven't tested this model yet in field, which is in real or even at a pilot scale. And we only like analysis, analyze how much each farm or the farmers will have an income, but we didn't analyze it how the consumers will be affected. For the future plans, we would like to have more scenarios, which means like more data for more years rather 2018. And also we would like to experience rather than just 2018 and 75% of the 2018, we would like to see like more dry scenarios. Also alternative government food price subsidies levels. So instead of just like 150% or 250%, we would like to do like more scenarios. And I heard also there is like a cost subsidy. So I would like to know more about that and then implement it in the model to see what the results will get. And again, as I mentioned, this model is only giving, the profitability and the income for the farmers, but not yet for the consumer side. And with that all, here are the references. If you have any questions, you may see my email in the beginning of the slides. Thank you so much, and you all have a great day.
Thank you very much, Dr. Dina, for that, and Dr. Frank for that presentation. With the indulgence of the conference, we're going to try to bring on John Lane here. We had technical difficulties before. It looks like his presentation is coming up. And John, can we hear you?
Yes, can you hear me now, Bill?
We can, yes. So if you could go through your presentation quickly, we'd appreciate it very much.
Salam alaikum. Thank you, Mr. Chairman, and thank you for the conference organizers for inviting us to present. I want to talk to you today about a novel method for electromagnetic imaging that may have application to water resources planning and well drilling in Iraq. The basic problem that we're trying to assist with is the traditional aquifer characterization by drilling versus geophysical methods. On the left-hand side of the image here, you see the bottom of an aquifer in the south central United States as defined by drilling, in this case about 100 boreholes, compared to the same area that is imaged with airborne geophysics. And you can see much higher resolution here when you go from approximately 100 boreholes to something like 100,000 airborne EM models. So clearly you can see the aquifer is better delineated, and areas that might be of interest for targeting for drilling, such as the paleo channel that's outlined here, can be revealed. But the issue is with drilling or ground-based geophysics. Here I'm going to talk about a time domain electromagnetic method where we lay a coil of wire on the ground and induce a current into the subsurface that will couple to conductors, and then we can use that information to generate a model that we can link to the local hydrogeology. So the issue here is one of scale. We can take this loop of wire that we can put on the ground and move around, and we can move it up to the air and tow it with a helicopter. We can also use fixed wing aircraft. And this could be a very efficient way to look at much larger scale problems than can be addressed with the ground-based geophysics. But we have, so why would we want to do this in an airborne sense? I have an example here of an electrical resistivity imaging method, another method that we taught in Iraq back in 2010. So here we can get about 1 kilometer of profile a day with the ground-based system. And we can compare that to what we can get from an airborne geophysical survey, where we can fly at about 100 kilometers per hour. So clearly, when we go to airborne methods, we can assess a much larger region, and it's more suitable for a regional type of study, whereas the ground-based geophysics can be very useful for a very local study or to answer a local question, such as where to site a well. But what we have is this problem of scales, what we can do with ground-based geophysics versus what we can do with airborne geophysics. is really a question of cost and the problem that we're trying to solve. And we have long sought another mobile method that would fill this unmet need for continuous imaging and profiling at more medium scales than could be addressed simply by ground-based geophysics or assessed regionally with airborne geophysics. And in conjunction with colleagues at Aarhus Geophysics in Denmark, they have developed a towed time domain electromagnetic imaging system for rapid subsurface imaging. It's the same concept. We have the transmitter here that I showed in a ground-based or helicopter-borne version. Now we're towing this with an ATV, or we can tow it with a small boat. So we have the transmitter, and then towed behind it is the receiver. And this gives us an opportunity to collect continuous profiles that it can image the shallow subsurface, something to the order of 100 meters in most cases. It does have some limitations. Electromagnetic coupling with power lines and pipelines and metal fences is a problem. It's most sensitive to conductive targets, such as clays and other subsurface features. And you need to be able to access the area that you're interested in imaging. So it can't be used in wooded, forested terrain. You need to have a fairly open area or a river to work on. But this technology does give us an opportunity to bridge the scale between the local ground-based geophysics and the airborne electromagnetic imaging scale. It bridges not only the spatial scale, but the cost scale of the different types of projects you might use for ground-based versus airborne imaging. This system that I showed you earlier, the images were of the prototype. Aarhus University has now commercialized the system. It has a slightly different configuration today than the initial prototypes. And I'm going to show you an example from a project we did in Western Tanzania. But before I do, I want to mention that there are other international vendors that are entering the market. So fairly soon, there will be more than one or two sources of instruments that can be applied to the commercial market. The example that I'm going to show you is from Western Tanzania. It's some work we did to try to improve the water supply for some refugee camps located on the border of Tanzania. This talk was initially presented at World Water Week last year in Stockholm. And my co-authors there are listed. So as I mentioned, we're working in Western Tanzania, which is in Eastern Africa. And we were interested in trying to solve water supply problems from several refugee camps. But not only the refugee camps, the project was broader than that. We were also interested in trying to assist the host communities who also suffer from fairly severe water stress. This particular camp is a Nyarugusu refugee camp that is supervised by the UNHCR. It has a population that varies, but it's around 80,000 people. And the refugees are primarily from the Democratic Republic of the Congo and Burundi, who have fled for various reasons: civil war, natural disaster, and generally poor economic conditions. This satellite image shows the imprint of the refugee camp and the impact of the refugee camp on the surrounding area. As I mentioned, the host communities are also suffering from severe water stress, and they are co-users of the resource. And so the idea was to not only to try to solve the water resource problem of the camp and to try to wean them off of surface water sources, but to provide an alternative and safe water drinking sources for the host communities. So what I'm showing here on the left-hand slide is the track line of the TTEM survey profiles that were conducted both within and in the surrounding camp. And what the goal was to locate some high production wells that could be used to support the camp, and as I mentioned, to wean them off of use of the streams that are in the vicinity of the area, because the use of, with such a footprint, 80,000 people, they were impacting the downstream users of the surface water. So I'm going to show you just a couple of examples of what the TTEM can provide. Essentially, it's continuous imaging along the track line, suitable for imaging to something on the order of 100 meters. What we see here in these profiles, the hot colors are more electrically resistive. In the superficial, we have a superficial aquifer that you can see with the resistive layer right at the top. We have a conductive layer, which are weathered materials and clays, overlying a more resistive bedrock below. And we can see this consistently throughout the areas that we profiled. And it turns out what we have in this area, we have a superficial aquifer where the water quality is fairly poor due to the intense use by the people in the camp. But underlying this, this continuous confining unit, we have the more productive aquifer. This is the northwest side of the camp. And on the northeast side, we see a very similar situation where we have the superficial aquifer separated by confining unit and the underlying bedrock below. And we use this information to target several wells in the area. But what we also, this profile data enables us to do is to come up, string these together and enable a 3D interpretation of the hydrogeology in the area, and able to provide this information to the decision makers along with suggestions of the most highly probable areas to drill. So what about production rates? We're averaging about 13 line kilometers of data a day in the refugee camps and in the surrounding communities. And as I mentioned, with 2D resistivity profiling, your productivity is limited to something on the order of 1 kilometer per day. So you get quite a boost in your imaging ability with the towed system versus the ground-based systems. So if I can compare these methods with the ground-based time domain EM, you get about 1 sounding per hour. Whereas the TTEM system, you can tow at 5 to 10 kilometers per hour, which is obviously can't achieve the production rates of a heliborne or fixed wing aircraft with the airborne survey. But you do achieve something on the order of 3 sounding every 3 meters with the TTEM system, which gives us the ability to do the continuous profiling. And it's suited for the shallow to medium depth aquifer scenario, something on the order of 80 to 100 meters. Whereas the ground-based TEM is labor intensive because everything is moved manually. The ability of the TTEM to be towed by an ATV or a boat, really gives us an advance that's somewhere in the intermediate between airborne and ground-based surveys. It has a much lower cost per sounding than the ground-based survey, and somewhat less than the airborne geophysical surveys. So in summary, this novel electromagnetic imaging method gives us an efficient tool for shallow aquifer characterization in the 0 to 100 meter range. It's fairly efficient because it's mobile, and it addresses the scale between the ground-based and airborne surveys. And it's not just a research tool, it is an emerging tool that has entered the commercial market, both as instruments and as a product that can be provided by engineering firms. It does suffer from the same limitations of airborne or ground-based survey in that because it's an electromagnetic method, it will couple to power lines and pipelines, requires open access, and it is most efficiently used in less electrically resistive terrains. So with that, Mr. Chairman, I'll conclude my talk and listed a couple of references there. And I greatly appreciate the contributors to this survey. Thank you.
Thank you, Dr. John Lane, for that presentation on a new hydrogeophysical method. And with that, that concludes the presentations from the U.S. Geological Survey and our collaborators today. I apologize, we have gone over our time today. We are available if you like for questions. We understand if we need to end the conference for today at this time. We thank you for the kind invitation. As I said in my introductory remarks, we very much value our past collaborations and hope to continue those into the future. So I will now turn it back over to the conference host.
Bill, did you hear me?
I did not hear you. I do now.
Okay.
No. Yes.
I'd like to say thank you very much for your efforts for chairing this session. Thanks for all your colleagues for their nice presentations and work. I'd like to ask the audience here if they have any questions to ask, if you don't mind.
Certainly, we don't mind.
Okay, thank you very much. عفوا اكو احد عنده سؤال يحب يسال؟ Nobody wants to ask. Thank you very much. Thanks again, and thanks again for your colleagues and your efforts. Thank you very much. Thank you.
Thank you.